Hi again. We're still working on mathematically tricky ice tables. So let's see what they have served up for us this time. This reaction is if you take hydrogen and iodine and combine them, occasionally some hydrogens and iodines will get married and make hydrogen iodide. And there's an equilibrium for that, of course. And they tell us they put a mole of hydrogen, and we are delighted to see it's a 1 liter vessel, so we're dividing everything by 1. 1 mole per liter of hydrogen and 1 mole per liter of iodine. They don't mention HI, so we assume we start with none. They put all that in a vessel and cook it at high temperature, and some time passes and they say, where do we land when we're at equilibrium? So we don't have an equilibrium number to solve for, so this is another algebraic one where we're going to say some amount of hydrogen reacts and some amount of iodine reacts. And do I put x here? Not quite. The ratio is 1 to 1 to 2, so this should actually be a 2x. And so the remaining hydrogen is 1 minus x. The iodine is also 1 minus x. And the HI is 0 plus 2x. Okay. And they tell us the equilibrium constant is 45.9. So when the system gets to equilibrium, we have our products, which are just HI, 2x and power of 2, over our reactants. They're both 1 minus x, so to save a little space, I'm going to write 1 minus x all squared. And they tell us at equilibrium that comes out to 45.9. And now we must solve this for x. Fast way is graph the left side, graph the right side, and then see where they intersect, but I'll pretend I can't do that, and we'll do this the algebra way. Square root both sides, because that will strip off this square and this square. So having done that, we have 2x over 1 minus x, no need for the brackets anymore, equals, and the square root of 45.9 is going to be 6 point something, 6.77. Now, we've got an x in the denominator, that's bad, and to get it out of there, I'm going to multiply both sides by 1 minus x. You can't just multiply by x or minus x, you have to do this entire term to get it out cleanly. So we do that. 1 minus x's cancel. And now we have 2x equals 6.771 minus x. The 6.77 distributes through the brackets, so it's going to hit the 1 and the negative x. 2x equals 6.77 minus 6.77x. Now, we want all our x's on one side, so this, having x on the left and x on the right is not good. To get rid of this, I'm going to say you can either take it to the left side and it becomes plus 6.77, or you can think of it as I'm adding 6.77x to each side of the equation. Both of those are valid. This cancels, so that's all gone. And we get 2 plus 6.77 is 8.77x equals 6.77. Divide by 877, and we get x equals 0.772. Now that we know that, we can go back to our ice table, and anywhere there's an x, we could put in 0.772. We could find the change numbers if we wanted, but all we really care about is the equilibrium numbers. So 1 minus 0.772 should be 0.228. Same value here. And 2 times 0.772 is going to be 1.544. A little risky doing that in my head. Let me, 772 times 2. Yeah, 1.544. So those should be our equilibrium numbers. Everything we were given here had 3 significant digits, so we're probably okay giving 3 digits here. I ran a bit of a risk only carrying 3 digits during my work. I should probably have carried 4 or 5 digits if I was going to give a 3-digit answer. So a little tentatively, I will say these are the equilibrium concentrations. And if you get a slightly different number carrying more digits, then you are good and I am bad. See you in the next one.